everybody, Mrs. White here. Today we're going to take another look at the end behavior of polynomial functions, specifically to look at how we can use symbolic notation, which is what you see over here on the right, to communicate what the ends of the graph are doing. In other words, as we look to the right and as we look to the left, where do we see the function heading? Is it heading up or is it heading down? So let's start off by reviewing what we know, and as we do so, we'll look at how this statement right here really just says the same thing we've been saying all along. So these first two rows right here talk about the end behavior of even degree polynomial functions. So here's two examples, x to the second, 2 is an even number, or negative x to the second, where that leading coefficient is negative. This could be an x to the fourth, an x to the sixth, any even degree when it's in standard form. And what we've seen is that if there's a positive leading coefficient, both ends head up like an upward facing parabola. If this was an x to the fourth, it might wiggle around a little more, but it would still do the same thing on its ends. And if we have a negative leading coefficient, then both ends will head down, being reflected upside down. So now, looking over here, what this really says, I'm going to read it first. It says, as x approaches positive infinity, f of x approaches positive infinity. So let's think about what this means. X is the left-right direction. So when we say we're approaching positive infinity, it just means that we're tracing the graph farther and farther to the right. In other words, we're moving to the right along the x-axis and we're watching the graph to see where it goes. When we say f of x, we're really saying y. Or in other words, we're talking about the function itself. Where is the function heading? And if we look at this graph, as we head to the right, we see that the y values, the function values, are getting higher and higher. So the function values are approaching positive infinity, meaning they're going higher and higher up as we move to the right. So all this statement really says is, as we move to the right, the graph goes up. And this one right here says, as we move to the left, because x is now approaching negative infinity, now the function again heads up toward positive infinity. And that's exactly what we're seeing here. As we move to the right, the graph goes up. As we move to the left, the graph goes up. This next one right here, we're seeing that the graph falls on both sides. So as we move to the right, the graph goes down. And as we move to the left, the graph goes down. Again, x, we're talking left and right, so positive would be right. F of x, we're talking y, so now negative would be down. As we move to the right, the graph falls or heads down. As we move to the left, the graph falls or heads down. These next two right here are really exactly the same thing, but now we're talking about odd degree graphs. So here is one that is a positive leading coefficient, so it kind of looks like a line with an increasing slope. So we are seeing that it rises on the right and falls on the left. In other words, as x approaches infinity, as I move to the right, the function is heading up, and as I move to the left, the function is heading down. One last one right here, it's really just exactly the opposite of the last one. Now, as x approaches positive infinity, the graph heads toward negative infinity, meaning as I move to the right, the graph heads down. And then this bottom statement says, as x approaches negative infinity, so as I move to the left, the function heads toward positive infinity, meaning it's heading up, and that would be that other arrow on the left. So this is just a way of saying where the graph is heading. Of course, we never really get there, but we're going to head forever in those directions as we follow those arrows. The rest of this video is really just meant to reinforce this idea by looking at how we can look at a graph and describe the end behavior, or how we can look at an equation and describe the end behavior. So let's start with the graph. When we look at a graph, we can definitely see the end behavior right away if we focus on the arrows. So I'm going to keep this color coding going. Notice when I look at the right side that this graph is heading up. And that's what this green statement says here. As x approaches positive infinity, the function heads toward positive infinity. In other words, as I head to the right, the graph is heading up. This second statement right here says as the graph heads left, it also heads up, and that's where I am seeing those upward facing arrows on both ends. One other thing we can do, this is really just reviewing what you've already done in previous lessons. We actually could do a little better now and look at this graph and even try to write a possible equation. And that's where we'll want to focus on these roots or x-intercepts that we're seeing and set them up as factors. So the first thing I noticed is that there's a root at 0. So I'm going to put just a regular old x out front. That's like x minus 0. And then I also noticed that there's 3 more roots. One of them is at -3, one of them is at 2, one of them is at 4. And so again, I set those up as factors as well, always x minus the root. And I chose to leave the exponent as 1 for all of these roots because I'm noticing that the graph is crossing through at every single root or x-intercept. So I should expect an odd exponent. And I'm going to do one final check and just make sure that this looks right. If I count up my x's, I'm seeing 1, 2, 3, 4 total x's. That's degree 4 because I would see an x to the 4th in standard form. And if I look closely at this graph, this looks a lot like an x to the 4th graph should. I see 3 turns. And the positive leading coefficient here means that the arrows would remain pointing upward. Let's look at one more example. This one right here. I can start off and notice that this graph is heading up if I look left, but heading down if I look right. So this is one of those odd degree graphs that had different directions on both ends. So here's a little practice with how to say that using end behavior. This really just says, as I move to the right, the graph goes down. As I move to the left, the graph goes up. And then I could piece an equation back together by looking at my roots and creating factored form. So I'm seeing the graph crossing at -4, touching, bouncing at -1, and then crossing at 3 and 5. So here's my factors that go with that. You'll notice the x plus 1 is squared because of the bounce at -1. And then the rest of them just have a 1 for an exponent. I also chose to put a negative sign out front because I can tell that since this ultimately heads downward as I move to the right, that there's a negative leading coefficient. I don't know what negative number it should be, but I know it's got to be negative. The last thing we'll do is just real briefly look at a couple examples that go the other direction. How can we look at an equation and determine the end behavior? And it really just has to do with looking at this equation, counting up the total x's so that I know the degree, and now I can start to picture what that graph should look like. So before I even try to describe the end behavior, I'm going to say I see 1 x right here, 1 right here. This is actually x plus 2 twice, so that's 2 more total x's if I were to expand it. So I actually have a total of 4 x's right here, which means this is degree 4. If there's a negative leading coefficient, I'm expecting a graph that looks something like this. Even functions should do the same thing on both ends, and the negative makes it go down instead of up. And now I can write my end behavior statement. As I move to the right, I'm heading down. As I move to the left, I'm also heading down. I could also do a little better and actually sketch this graph without using a calculator by plotting my roots and then making the end behavior happen. And this is something you've already practiced, but here it is again. -4 is my first root, and it's crossing because the exponent is odd. +5 is another one, and again, it's crossing because the exponent is odd. And then -2 is my third root, but it's a repeated root, and that's my cue to bounce off there instead. Just a reminder, if you were going to graph this yourself, you might want to put the arrows on the graph before you try actually drawing the polynomial curve. I like to plot the roots, place my arrows on the graph, they're both heading down, and now I can draw my curve in a way that it heads and crosses through at -4, turns around and bounces at -2, and along the way turns around so that it can cross right through at 5. One last example right here. This one has 3 x's, so that's degree 3. The leading coefficient is positive, and so now I can start to get a sense of how this graph should head upward like a line, which lets me know that as I head to the right, the graph goes up. As I head to the left, the graph goes down. And just like in the other, I can plot my 3 roots. One's at 0, one's at -3, one's at +2. Plot those on there, place your arrows, and now I can draw a curve that perfectly crosses through all 3 x-intercepts. So again, this has just been a summary of what we've been exploring so far, with one new addition of how we can use symbolic notation to communicate what the ends of a polynomial graph are doing. Thanks for listening.